one of the easiest ways for us to think about it is that there's two types of things that could become unavailable, or two types of failure zones. So one is a whole node goes out. So in a traditional, well, I should describe sort of how we are doing distributed storage, but there's two standard ways. So one is just replicas. So you might have 3 replicas of the same object across different nodes. And then another way is erasure coding, but erasure coding is basically the same thing. You just might split up a single object into, say, 12 or 6 different pieces and store those on different 12 or 6 different nodes. So one unit of failure is a node. So when we say a node, it could be the node, exploded, or more typically, it's just the network is cut, or some component of it is out that makes it, unusable. And then the other type of component is a disk. So inside a node, you have multiple disks, and they may be virtualized, or you might have some sort of protection at the hardware level at RAID or something like that. But at its core, it's a single disk or volume. So back to what the operator does with the failure management then is you have to think carefully about when each of those, when say a node is unavailable, what do you do, right? So the standard thing in Kubernetes would be, let's just start up a pod on a spare node and then go forward, and all is good, right? We wanted 3 pods, we had 2, we created 1 more, and boom, we're all good. And that in principle that's fine, and it works okay and for stateless applications. But as people in storage well know, for when you're dealing with a lot of storage and disk, that is a high cost operation, right? You have to then migrate your data onto this new pod. And so with an operator, then you could think about what sort of knobs do you want to have, or configurations, or other types of flexibility to allow the user to configure that. So one obvious one is, how long do you want to wait before giving up on this node and then migrating it to another pod? So in what happens in production systems often is you get glitches, right? Someone turns off the power periodically, or you have a network glitch, and then your alert systems, monitoring systems start beeping that this is offline. But then, if you just hold off and wait 3 minutes, 5 minutes, then all is okay, right? So that's one type of control, right? That you want to have a simple, what we call rebuild timer. And that's one of our configurations in our CR that you could set up, and it controls at the operator. There's other questions about how does the operator assess whether the system is available or not. So in a distributed system, it's not a trivial answer of just counting, seeing that all nodes are up, or all pods are up, or all pods are down. It's, we're dealing with different consistency levels of data. So you might have a strong consistency level where you want to make sure that what you read is what you have previously written, or you might be willing to have an eventual consistency model where it's not so critical that the data that you read has been written immediately, as you might be able to be willing to accept a lag. So for our storage system, you could have multiple ones of these, what we call storage policies, all in the same system. So you could have, one set of S3 buckets say, these are eventually consistent, we're just saving them for log data, but these are banking transactions or other type of critical data that we need strongly consistent. And those are all overlaid and put on the same data, on the same underlying storage. So
nice.
How do you assess that and manage that? So that's a lot of the logic that goes into the operator naturally. So in our standard system, this would be at a more of a control layer, but with Kubernetes, we could take advantage of the Kubernetes sort of reconcile loop or the management loop, and then be able to take care of a lot of that at the operator level. So so that's part one of the story. Sort of please interrupt me if I'm going off too much on a side note, but
no, this is awesome.
Okay, so in the normal case, you have that simple question of, I'm going to wait, say, 1 hour, 60 minutes before migrating a pod. And then there's another question of, maybe I don't even need to migrate that pod. If I already have enough redundancy from my erasure coding and my storage policy allows it, then I'm just going to leave it and then wait for it to recover, or wait. We're doing alerting at the same time. So then we might want to require human or user intervention to decide what to do as best. And then what if there is no spare capacity to spin up a new pod, right? That's another question, right? So if you're not dealing in a elastic, say, public cloud environment where you could just spin up a new VM, this becomes an issue, right? So in enterprises, they have fixed number of, here's your 12 physical nodes, that's all you have, right? So use it all. So if something goes wrong, then what, right? So that's another question that we're working on to operator to figure out and sort of parameterize what can be done in those different cases. So that's one of the considerations for node failure. There's other things like cascading failures. So you're dealing with one pod failure and then another pod goes down. So what do you do then? So there's also questions like that of what to do, which we're taking in all our experience from our large clusters and our production experience to apply to that. But I wanted to get to the other part, which is kind of interesting, is where a disk fails. So if you look at our object storage systems in production, this is the most common error condition, right? So disks die, right? You could see the survey that something like 2% of disks fail over 1 year. So when you're talking about storing petabytes of data, we're talking about disk failing daily or even hourly for certain things. So one aspect is you of course design your system to be resilient to those types of disk failures through redundancy and even hardware RAID and other mechanisms like that. So ideally, you want the situation where the operations guy, right? He doesn't get beeped in the middle of the night, but comes in at 9 a.m. say, this disk is broken, this disk is broken. Pop it out, slide one in, and you're all good to go until the next day. So in a Kubernetes sort of managed type environment, the operator needs to look at what happens when a disk fails as well. So I see a lot more in the Kubernetes environments where the disks are virtualized, where a single physical disk failure could affect multiple virtual volumes, PVs, right? So there's different aspects of what we want to do there. So for example, if a disk fails in a single node, and then there's spare capacity on that same node, we just want to, mark this guy as bad, this PV as bad, and just recreate a new PVC on that same node. And then at the worst case, if there's no spare capacity, or if multiple PVs are bad, then we want to, again, think about migrating to the pod to a new location. So these are the types of logic that the operator is taking care for us right now. So so I would say, for our operator, probably 90% plus of the sort of code and the logic is really around this failure management and failure handling, which is as it should be, I suppose.